In this Pencast, we show how to calculate the autoregressive model parameters for parametric spectral estimation. Suppose we have a wide-sense stationary stochastic process defined by the autocorrelation function given in this slide. We are asked to assume an autoregressive model of order 2 and to find the corresponding model parameters. But since the model order is 2, we need to estimate p plus 1 parameters. And these p plus 1 parameters are A1, A2, and the variance of the input noise. In this Pencast, we will show how to obtain these model parameters by two methods. The first method is by using the Yule-Walker equations, and the second method is by using FIR Wiener solution for the one-step linear predictor. Before we start, note that since we need to estimate three parameters, no matter which method we choose, we need an estimate of the autocorrelation function for three lags, that is at lag 0, at lag 1, and at lag 2. In this case, the autocorrelation function is exact, so in principle we can recover a true estimate of the power spectral density. And from the formula given here, we can easily calculate the autocorrelation at lag 0, which is equal to 1, at lag 1, which is equal to 1 over 2, and at lag 2, which is 1 over 4. Okay, then let's start by showing the Yule-Walker method. For autoregressive models, the Yule-Walker equations reduce to a linear system, given by the autocorrelation matrix and the parameter vector. To write the autocorrelation matrix, it is useful to remember that it has a template structure, which means that the values on the diagonals are the same. So you can see here that the main diagonal is all R0, and these diagonals are all R01, and these diagonals are all R02. In the Yule-Walker equations, the autocorrelation matrix multiplies the parameter vector, and this matrix multiplication is equal to a vector composed of the input noise variance in the first positions, and zeros in all other positions. Once we have written the Yule-Walker equations, we can substitute the estimated values from the autocorrelation function. Again, here we have an exact function, but in practice we will need to estimate these values from a windowed random signal. Once we have plugged in the values of the autocorrelation, we can write a system of equations. From the first line, I can write that 1 plus 1 over 2a1 plus 1 over 4a2 is equal to sigma I squared. From the second one, I obtain 1 half plus a1 plus 1 half a2 equal to 0. And finally, from the last one, 1 over 4 plus 1 over 2a1 plus a2 equals 0. Now I can solve the system. From the last equation, I obtain that a2 is equal to minus 1 over 2a1 minus 1 over 4. And if I plug this into the second equation, I obtain that a1 is equal to minus 1 over 2. And thus, a2 is equal to 0. Finally, from the first one, I obtain that sigma squared is equal to 3 over 4. So my estimated model parameters are a1 equal to minus 1 over 2, a2 equal to 0, and noise input variance equal to 3 over 4. After showing the Yule-Walker approach, we can see how to obtain the same solution by using a one-step linear predictor. Briefly recalling Wiener filters for the FIR case, the optimal filter coefficients can be found by this formula, which basically is the matrix product of the inverse of the autocorrelation matrix of my observed signal times a vector representing the cross correlation between the desired and observed signals. And the filter error can be calculated by this formula. For a one-step linear predictor, the autocorrelation matrix is obtained from the observed signal shifted by one sample, because the goal of this filter is to predict the current samples from a linear combination of the past samples. So the input to the filter is a delayed version of the observed signal, while for the cross-correlation vector, the desired signal is x of n, and the input to the filter is x of n minus 1. So we are cross-correlating the signal with itself shifted by 1. So it's equivalent to calculating the autocorrelation shifted by 1. And this means that we use lags 1 and lags 2. The other important feature of the one-step linear predictor is that the filter error is white noise. So once we have defined the autocorrelation matrix and the cross-correlation vector, we find the filter coefficients by this matrix product. Remembering a little bit of basic algebra, to inverse this matrix, we need to calculate the determinant, which is 3 over 4 in this case. And then the inverse is given by the inverse of the determinant times the matrix of cofactors. From this matrix multiplication, we obtain 1 over 2 and 0. But remember that this filter is actually the inverse of the innovation filter. Thus, we need to invert the sign of these coefficients to find the autoregressive model parameters. Finally, to find the input noise variance, we calculate the filter error like so, from which we obtain 3 over 4. So also in this case, we find A1 equal to minus 1 over 2, A2 equal to 0, and sigma I squared equal to 3 over 4. Once we obtain these model parameters, the ultimate goal is to estimate the power spectrum. So all we need to do is to write the formula for the power spectral density of an autoregressive model, and then by simple passages, first we substitute sine and cosine for the complex exponential, and then we obtain the modulus squared of this expression, and finally we have the power spectral density that is given by 3 over 4 times 1 over 5 over 4 minus cosine theta. And with this formula, I can now plot the power spectral density at any theta and at any resolution I want. It is actually a continuous function. So here I make a schematic drawing, and to do so I make a few quick calculations. First, I can notice that the maximum of this function is in 0 because the cosine is maximum, and thus the denominator of this function is minimum. And if I plug in 1 for the cosine, then we obtain 3 at theta equal to 0. Then I could make it as detailed as we want, but for the purpose of this pencast, I will just calculate the values at plus minus pi over 2. And if you put 0 for the cosine, then you obtain that the power spectral density is 3 over 5 at plus minus pi over 2. So it is somewhere over here. And then I can quickly draw the power spectral density. So as homework, you are welcome to repeat this procedure for a stochastic process defined by the autocorrelation function given in the formula in this slide. This concludes this pencast, in which we show how to calculate the power spectral density from an estimate of the autocorrelation function at given lags, assuming an autoregressive model as the data generating process. Thank you for listening.